Physics happening inside your chest right now, it is nothing short of a microscopic miracle. In this explainer, we're going to explore the hidden physical forces governing our lungs and the incredibly complex biological fluid that literally keeps us alive with every single inhale and exhale. So this brings us to a really fundamental question. Have you ever wondered why your lungs don't just completely collapse every time you exhale? Think about a wet plastic bag. When you press the sides together, the moisture makes them stick super tightly, right? Well, your lungs are full of millions of tiny wet air sacs called alveoli. When you breathe out and those sacs shrink, there are these powerful, invisible physical forces acting on them that just want to snap them completely shut, yet they stay open. How is that physically possible? Okay, let's dive right into this. In this explainer, we'll hit 5 key sections. Section 1, the surface tension problem. Section 2, the law of Laplace. Section 3, surfactant, the biological hero. Section 4, increasing lung compliance. And finally, Section 5, neonatal respiratory distress syndrome. All right, kicking things off with Section 1, the surface tension problem, the hidden force in your lungs. To truly understand how the lungs work, you have to understand the thin layer of fluid that lines them. You see, surface tension is created by the intermolecular forces between the liquid molecules lining your alveoli. Because these liquid molecules are highly attracted to one another, they constantly want to pull together. In the spherical shape of an alveolus, this creates a relentless inward pulling pressure. If left unopposed, this surface tension would be so remarkably strong that it would completely collapse the air sacs. And that is a dangerous condition known as atelectasis. Which brings us to Section 2, the law of Laplace, the math of lung collapse. This collapsing force isn't just a biological hurdle, it's a strict mathematical one, perfectly explained by the law of Laplace. This law tells us that pressure equals twice the tension divided by the radius. In plain English, if surface tension stays constant, as the radius of an air sac gets smaller, the collapsing pressure actually goes up. So the crucial takeaway here is what happens when you compare large versus small alveoli. Without any biological intervention, a large alveolus naturally has a lower collapsing pressure. But a small alveolus, with its tiny radius, generates a massive, dangerous collapsing pressure. Think about blowing up a balloon. It's incredibly hard to get it started when it's small, tight, and unstretched, but it gets way easier as it expands, right? Because of this exact principle, our small alveoli are highly prone to atelectasis, or complete collapse if absolutely nothing is there to break that surface tension. That brings us to our solution in Section 3, surfactant, the biological hero. Fortunately for us, our bodies have evolved a truly amazing molecular solution to neutralize this physical threat: pulmonary surfactant. This life-saving fluid is synthesized by specialized microscopic factories in the lungs called type 2 alveolar cells. It's a complex mixture of phospholipids and proteins, but the absolute star of the show is a specific lipid with a very long name, dipalmityl phosphatidylcholine, or DPPC for short. What makes DPPC so incredible is its amphipathic nature. One end is hydrophobic, meaning it hates water, and the other is hydrophilic, it loves water. These DPPC molecules align themselves perfectly on the alveolar surface, pushing their way between the liquid molecules and breaking up those attractive forces. By doing this, they dramatically lower the surface tension, effectively neutralizing the danger posed by the law of Laplace. But, the DPC lipids don't work alone. They are backed up by 4 unique proteins, SPA, B, C, and D, that facilitate this whole process. And they have highly distinct vital roles. SPB and SPC are sort of the molecular architects. They're smaller proteins absolutely key to organizing those DPC molecules into a perfect functioning film layer. Meanwhile, SPA and SPD belong to the collectin family of proteins, and they act like biological security guards. They are heavily involved in our innate airway immunity, basically fighting off microscopic invaders in our conducting airways and alveoli. Plus, SPA even helps regulate the recycling of surfactant back into those type 2 cells. It's an incredibly well-oiled machine. Let's see what this means functionally in Section 4, increasing lung compliance, making breathing easier. Now that we know what surfactant is made of, let's explore how it fundamentally alters the physical mechanics of breathing. When scientists want to isolate exactly what surface tension does, they conduct a brilliant experiment, measuring the pressure and volume of an animal lung when it's distended with air versus when it's distended with saline, which is basically salt water. The vertical axis shows lung volume, and the horizontal shows the pressure needed to get there. Let's contrast what happens. Filling the lung with saline effectively removes the air-liquid interface, reducing surface tension to near zero. So the pressure required to inflate the saline-filled lung is solely overcoming the natural tissue elasticity of the lung itself. But look at what happens with air. It takes significantly more pressure to inflate the lung with air because you're fighting both tissue elasticity and surface tension. Also, notice that wide looping gap between the inflation and deflation pads on the air curve. That difference is a phenomenon termed hysteresis. It's incredibly obvious at small lung volumes, again proving that surface tension is a massive physical barrier to inflating collapsed or small air sacs. Bringing this all back to our daily lives, surfactant greatly increases lung compliance. And compliance is just a fancy way of measuring how easily the lungs stretch and expand. By drastically lowering that surface tension, surfactant fundamentally reduces the physical work required by your respiratory muscles to expand your lungs during inspiration. Without it, you would be absolutely exhausted just trying to take a single breath. And as an amazing bonus, this lowered surface tension also helps prevent pulmonary edema. If surface tension were left completely unopposed, it's been calculated that it would generate a 20 mm mercury force. That is a force strong enough to literally suck fluid right out of your blood vessels and flood your alveoli. No way we'd survive that. Which brings us to our final part, Section 5, Neonatal Respiratory Distress Syndrome, the clinical reality. To truly grasp how vital this physiology is, we have to look at the heartbreaking medical reality of what happens when this crucial molecule is missing. In a developing fetus, the timeline for surfactant development is incredibly strict. Surfactant synthesis by those type 2 cells doesn't even begin until around gestational week 24. And it isn't reliably present in sufficient life-sustaining amounts until around gestational week 35. This creates a really critical biological danger window. If an infant is born prematurely, especially between weeks 24 and 35, their surfactant status is highly uncertain. This lack of surfactant triggers a deadly domino effect, resulting in neonatal respiratory distress syndrome, or NRDS. Step 1. The premature infant lacks surfactant. Step 2, because of this, they immediately face unopposed sky-high surface tension. Thanks to the law of Laplace, those tiny newborn alveoli face massive collapsing pressures. Step 3, widespread alveolar collapse, or atelectasis, occurs. Because these collapsed sacs aren't ventilated, they can't participate in gas exchange. Blood just flows right past them unoxygenated, a dangerous process called a shunt, which leads to Step 4, life-threatening hypoxemia, or low blood oxygen. Lung compliance plummets, and the newborn's work of breathing becomes impossibly, fatally high. And the clinical reality is even more complicated than just collapse. NRDS is also historically known as hyaline membrane disease. A major compounding factor here is the dangerous retention of fluid in the lungs. During fetal life, pulmonary epithelial cells actually secrete fluid with chloride. At birth, there's supposed to be this immediate biological shift to sodium absorption via epithelial sodium channels, or ENOCs, which absorbs that fluid out of the lungs. But in premature infants with NRDS, prolonged immaturity of these ENOC channels prevents proper fluid absorption. So these tiny patients are not only fighting massive surface tension to open their collapsing alveoli, they are also struggling against excess fluid filling them. It's a double whammy. Thankfully, modern medicine stepped in. Today, surfactant replacement therapy, where we literally deliver carefully formulated surfactant directly into the lungs of premature babies, successfully saves countless lives by restoring that exact physical balance we've been discussing. But that leaves us with a fascinating medical mystery to ponder as we wrap up. Surfactant replacement works absolute wonders for premature infants. Yet, interestingly, clinical trials using this exact same therapy for adults experiencing acute respiratory distress due to surfactant dysfunction have consistently failed to show the same success. Why does this physical miracle cure work so perfectly for babies but completely fail in adults? It's a deeply complex physiological puzzle that medical researchers are still trying to solve right now. Thanks for joining me on this explainer. I really hope it gave you a new appreciation for every breath you take and keeps you questioning the incredible science inside you.